right, before we start solving problems involving trees, well, we'll need to learn some terminology about what the tree data structure is and what its parts are. And it'll be pretty brief. Want to keep it nice and simple, and then we'll start getting into more specific trees and problems involving trees. So, what is the tree data structure? The tree data structure is actually fairly simple. If you ever seen like a family tree, like a family chart, where you have like parents and grandchildren and cousins and things like that, then you already know what a tree is. You've already seen one before. So we trees are made up of nodes. All right. So here's a node, and inside the node is a value. I'm going to put 1. Does it have to be a number? No, of course not. It can be whatever value you so well please. It's just numbers just happen to be the thing that most people show. But each circle here is a node, and nodes can have children. So, for example, I could have this node here with a child 2, and then another child with a value of 3. Voila. So again, like if you've seen a family tree, then this should look familiar, right? You have like the mother and the father, and they have children, things like that. Now, trees in general, right, are essentially there's no restriction necessarily on how many children a node could have, unless it's a specific kind of tree. So we're going to get into different kinds of trees later on, like binary trees and binary search trees and all that kind of stuff. And so more specific trees have certain limitations on how many children a certain node can have and things like that. But a tree in general, there's no such thing. So for example, I could have this first node have like 3 children, and that's fine. Nodes can have their own children. So you can have grandchild nodes. So here's 4, and then here's 5, and then here's 6, and there you go. All right, so it can go on and on and on. And like I said, when we learn more specific trees, there will be restrictions and rules as to, where can you add new nodes, how many children can a specific node have. But right now we're talking generally, all right, and so we're just talking about the parts of the tree. Now, the topmost node is called the root node. All right, the root node is the node that all other nodes are descended from. Okay, so even if this tree were to go down, way, way, way more, 1 here is the root node. The nodes at the end of the tree, okay, so all the way at the bottom, are leaf nodes. Okay, so here are the leaf nodes. Okay, they're at the very edge. So at the very top is the root, at the very edge are the leaves. In between each node, you have these little lines I keep drawing, right? These are called edges. Okay, so this is an edge. Okay, so there's an edge from 1 to 3. There's an edge from 3 to 6. Okay, and again, I named the nodes by the value that they hold just for convenience sake. So we now know what the root node is. We know what leaf nodes are. We know that there are edges between nodes. Okay, so the edges kind of tell us how we go from one node to the next. One cool thing about trees that makes trees different from graphs is that they're in a specific direction. So if I go from 1 to 3, I'm not going back from 3 to 1, right? I go from 1, then I go to 3, then I go to 6, and then it's the end. Tree data structures are great for searching. Tree data structures are also good for modeling games. Like if you have like quests and things like that, where you do this first thing in the quest, and then you have like kind of a choice, and then you could do one thing or the other, like a choose your own adventure game. Trees will be great for that. Now, trees also have a height. All right, so basically we start at the root node and we count the edges to the leaf node. So here's the first edge. Here's from 1 to 2, and then from 2 to 4, here's another edge. All right, and you go to the leaf node. So even if the tree, like the way I drew this tree, all the leaf nodes are on the same level, but it does not have to be the case. So you go down to the lowest level, and then you count the number of edges. Here, the height, okay, is equal to 2 because there are 2 edges from the root node all the way down to the leaf node, the lowest leaf node. All right, so these are the different parts of a tree. It's very important that you understand this vocabulary. Please don't skip out on vocabulary. I know it seems like an easy thing to feel it's not important, but you can't understand problems if they start talking to you about edges or like, count the number of leaf nodes or things like that if you have no idea what they're talking about. All right, so it is important to grasp this vocabulary. We'll deal with more vocabulary later, but this is a light introduction to trees, so I wanted to keep it short and simple. All right, so now that we've learned some more about the basics of trees, I want to talk specifically about a subsection of trees, a certain kind of tree, which we're going to talk about specifically binary trees and binary search trees. Hi, my name is Jonathan Hopp, and if you're enjoying this tutorial, I invite you to visit my website, codingyourcareer.com. I've got courses on Java, JavaScript, TypeScript, and all of the famous frameworks like React and Angular, the kind of things you'll need in order to break into the world of tech and get the knowledge that you need. It's even great for people who are already in tech and want to level up their skills. So it's codingyourcareer.com. Let's continue with the tutorial. All right, now let's discuss a specific kind of tree or a subset of trees called binary search trees or BSTs. Binary search trees are very efficient for looking up numbers. So data structures are all about how do we arrange data in a way that is convenient for us to get the job done. So for example, if I had a engineering requirement where I was given a bunch of numbers and I needed to find a way to search for numbers really quickly. All right, I could use a binary search tree to accomplish that task. But what are they? So as you can see, definitions are very important. Please do not skip over definitions or think that they're just side things. Definitions are how we understand what data structure we're dealing with and why it's good for our situation and why it might not be great for other situations. So binary trees are any tree where a node has no more than two children. All right, so binary trees, for example, the one here on the left is a binary tree. Each node has no more than two children. So, for example, this node has no children, but that's fine. This node has two children, that's fine. This node has two children, that's cool. So, none of the nodes violate the basic principle. Now, on the right, this is not a binary tree because this first node has three children, and that's a violation of the rule. All right, so that's really all it takes to be a binary tree. So, what's a binary search tree then, Jonathan? Why? We're going even deeper now. A binary search tree is still a binary tree, but it has an additional stipulation that the values have to be in a certain order. Let's kind of go into it. Let's say I have a node and the value of this node is 10. In a binary search tree, all the nodes to the left of 10, meaning all of its left nodes, all on this side over here, are going to be less than 10. Everything to the right will be greater than 10. And if that rule is ever broken, it is no longer a binary search tree. So for example, let's say this has two nodes. This is 5, this is 20. Cool. That follows the rule. This left node is 5. This right node is 20. 5 is less than 10. 5 belongs on the left. 20 is greater than 10. It belongs on the right. Now, as we add more children, we still have to follow the rules. Everything on the left side, from the perspective of the root node, has to be less than 10. Everything on the right, with respect to the root node, has to be greater than 10. No duplicates. For any individual node, the left node has to be less than the parent, and the right node has to be greater than the parent. So, keeping with that in mind, for example, we can do this. We can have 4 on this side. 4 is less than 5, so it's 5's left child. 4 is also less than 10, so it belongs on this side of the tree. Over here, we could have 8. 8 is greater than 5, so 8 belongs on the right-hand side. So the left child of 5 is 4, the right child is 8. 8 is less than 10, so it belongs on this part of the tree. If we go on this side, all right, then we can say, okay, cool, we can put 30 here, right? That's fine. 30 is greater than 20, so it belongs on the right. 30 is also greater than 10. So this tree is a binary search tree because all the nodes to the left of the root node are less than the root node. All the nodes to the right of the root node are greater than the root node. Each individual node, its left child is less than that node, and its right child is greater than that node. Now, it takes a little bit to get the rules down, but I find if you actually draw out a couple trees and ask yourself, is this a binary search tree or not, then that will help you. So let's kind of do that for a second so we understand how that works. Here I have put some example binary trees out here, and we're going to see if they are binary search trees. All right, so keep in mind, remember, binary tree is where each node has no more than two children. Okay, and then a subset of binary trees is binary search trees, which has all the rules I just talked about. So your job is to pause the video and tell me is the one at A, I'll mark it. This is A and this is B. All right, so there's a tree at A and a tree at B. Let me know, pause the video, think about it. Are A and B binary search trees? And if they are, why? If not, why not? Okay, pause the video and think about it. Okay, so let's look at A. The root node is 20. Okay, 15 is less than 20. That checks out. It's the left child, so 15 is less than 20. 25 is greater than 20, so it belongs to the right child. So this level checks out. Next level, 10 is less than 15, which is also less than 20, so it belongs here. That checks out. This is a 17, so 17 is greater than 15, but it's also less than 20, so it's on the left side of the tree, but it is greater than 15, so it does belong as the right-hand child for 15, but it's still on the left side of the tree because it's less than 20. Good. 25 is greater than 20. 22 is less than 25, so it's the left child, but 22 is also greater than 20, so it does belong on the right-hand side. So this checks out. Okay, so I'll put a little green mark. This is a binary search tree. What about the right side? Okay, we've got 100 as the root node. 200 is greater, so it belongs on the right. That's correct. 90 is less than 100, so it belongs on the left. So this first layer is correct. Let's go to the next layer. 85 is less than 90. That's fine, so it's the left child. 85 is also less than 100, so that's fine. But here we have 105. 105 is greater than 90, so it should be on the right hand of 90 on the right side. But 105 is greater than 100. So this node right here is not in the correct spot. Okay, this 105 is greater than 100, so it should be on the right-hand side of the tree, not over here. All right, so even though we don't even need to look at the rest of the nodes now, right? We found the node that was out of place, and it looks like B is not a binary search tree. All right, so it was very important to kind of do this so that we understand what the rules are and you can identify what a binary search tree is. Now, let's actually use a binary search tree to search for a value. All right, now binary search trees, well, they're for searching, so let's do that. Let's say I have a target number of 34. That's why I have t equals 34 over here. I would like to see if 34 is in this tree or not. Now, keep in mind, I know for a fact that yes, you can just look at the tree and see, but remember, in real life, these binary search trees might be pretty huge, so you would not be able to just look at them. Also, it happens like in the background, so the computer has to basically start from the top and work its way through the tree until it finds the number that we're looking for. Now, there's two options. Either the computer will find the number 34 somewhere in the tree, in which case it'll be like, hey, I found it. Or if it doesn't find the number 34 somewhere in the tree, it will return a -1. Okay, so that's just to kind of give you an idea of what the computer's behavior is going to be. So here's where binary search trees shine. Basically, they save us work. Picture a treasure map. Like if you're thinking about like one of those like old pirate novels where they have a treasure map and you go to find the treasure. Well, the point of the map is to tell you exactly where you're going. Kind of binary search trees are kind of like that. They don't tell you exactly where you're going, but they do cut out a lot of the waste. So for example, if you didn't have a map, right, and you tried to go somewhere, you could waste a lot of your time going to places that are nowhere near your destination. You wouldn't even know it. You would just have to like wander around and search every corner until you just hopefully hit the treasure chest. If you have a map or at the very least some kind of like way of looking at the environment, you can just tell yourself, well, there's really no point in going this direction or that direction. So I am instead going to focus on just these areas, and that will save you a lot of time in saying getting closer and closer to your goal. Binary search trees work the same way. They cut out uh, unnecessary work. So let's start by finding 34. Let's do the algorithm. First off, my first node, 100. Is 100 equal to 34? It's not. Okay, so we haven't found it yet. All right, now we have a choice. Do we go left, down the left side of the tree, or do we go down the right side of the tree? Well, by definition, everything to the left node is going to be less than the current node, and the right node is going to be greater than the current node. Is 34 less than 100? Yes, 34 is less than 100. So we should go down the left. That has the bit that is going to be, if 34 is somewhere in this tree, it's going to be down the left. That basically means there's kind of no point in even going this direction, right? Why iterate over it? It's greater than 100. 34 is less than 100. There's no point. So that, like literally, that's these three nodes, 130, 123, and 178. We don't even have to bother with them. There's no point in searching through them or wasting our time iterating through them because we know for a fact that they don't have the answer. If you were here for the video on binary search, if this sounds like a familiar strategy, it's because it is, all right? So being able to cut out the search space is going to save us a lot of time. All right, so we go from 100 along this edge to 50. Okay, great, now we're at 50. Is 50 equal to 34? Nope, 50 is not equal to 34. Okay, is 34 greater than or less than 50? Remember, there's no duplicates, so if it isn't equal to it, we haven't found it. So is 34 less than 50 or greater than 50? It's less than 50, so we're going to go down to the left side. Okay, which means we don't have to bother with this at all. That's work we don't have to do. See how much work we're saving? Every time we iterate across a node, every time we traverse the tree, we're saving work. Like everything on the right, who cares? Okay, we're at 25. Is 25 equal to 34? Nope, it certainly is not. Now which way do we go? Is 34 greater than 25 or less than 25? It's greater than. So nope, don't need to go to the left. There's nothing there for us. We're going to go to the right. Bam, we found it. Okay, we got to our node. Here's 34. There we go. We had to go 1, 2, 3 across 3 edges to get to our target. And look at how much work we did not do. We literally just skipped 5 nodes. Okay, 10, 67, 123, 178, and 130. Who cares about them? Because we knew by the way the tree is structured, there's no point in looking at them. Okay, and this is the power of the binary search tree. Picture if this tree were not ordered like this. Picture if the tree just was still binary, but wasn't in any particular order. Then you would have to search the entire tree in order to find something. So arranging the numbers in a specific order using the rules of a binary search tree cuts out a lot of excess work. Now, Jonathan, what would have happened if the target number were 35 instead of 34? 35 is not in this tree. What would the algorithm do? Okay, well, I'm not going to repeat the whole algorithm from the beginning. You kind of get the idea. We would be at 34, right? So we would say, okay, 35 is bigger than 25, so go here. Is 34 equal to 35? Nope. Then we go to the right. But there is no right. There's no further nodes. This is the leaf node, so there's nothing else. So in which case we would return -1. The algorithm doesn't change. It's just basically say, hey, I've reached a leaf node. There is no left node and there is no right node. There's nothing more for me. Okay, it's null. So I stop here and return -1. All right, so what is here's the classic question with all algorithms we have to ask, what's the big O? Okay, how does this scale? Okay, if I were to have a bigger and bigger and bigger tree, okay, remember this is a very small tree. In real life, these trees could be like, really deep, okay, with layer after layer after layer. So what's going to be the big O? How well does this scale with more inputs? Well, one of the things you can look at is it depends on the tree, but this tree specifically, you're going to think of it like this way. Every time you make a choice of whether to go left or right, first off, it's a binary choice, right? There's only 2 options. And every time you iterate or traverse from one node to the next, you're taking how many things you have to search through and cutting them in half. So here's what I mean by that. We started at 100. We have 2 options, but we cut off one because of the rules of the binary search tree. So that's halving our search space. So all this is cut off. And then we go here, and then we have it again, and go here, and we have it again, and go here. So we're constantly doing half, 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 half. I know it's not perfectly half. It doesn't have to be perfect. We're just generalizing. So therefore, the big O of finding a node within a binary search tree is going to be big O of log n. Okay, so logarithmic, like you're going to be doing halving the whole time. However, I want you to think about this a little bit because a lot of times when people draw trees, they draw them like nice, right? Where everything's got like, 2 nodes and things like that. There is an exception to this big O, and it does depend how the tree is made. So I want you to think about it for a second. I'm going to show you in a moment. You could have a binary search tree where the big O is not O of log of n. That is possible, right? Take a moment and think about it. Okay, remember, the tree doesn't have to be drawn this way. We can draw the tree a different way and still satisfy the rules of binary search trees. Okay, I'll show you what that looks like. What if we had a tree that looked like this? Does this break any rules? Okay, each node has no more than 2 children, so it's a binary tree. Okay, each node has no more than 2 children. Everything to the left of the root node is less than the root node. Okay, and each child is less than the immediate parent. So this is a valid binary search tree. All right, but you'll notice that it's all kind of in a line. And so what's the big O of finding 10? Well, let's say I want you to find, as if like the target is equal to 10. What would it take to find it? Well, John, that means we have to go the worst case scenario, like actually not even 10. The worst case scenario would really be like finding 11, like finding something that isn't even in here. In which case you go all the way down the tree and then you stop because there's no more, right? So that means you had to iterate through every single node in the binary search tree, which means that your big O is O of n. Okay, so one little thing about binary search trees that does trip up beginners is that the way that they're structured could affect their big O. Okay, so whether or not it's balanced or complete or things like that doesn't matter. If you have a binary search tree that's all one line, then you're kind of not gaining anything in terms of scale, mainly because it's still linear, right? Like if I add another node to this binary search tree, even left or right from here, that's one more node, right? That's linear. Every node I add is going to add like one extra unit of time in order to traverse the whole thing, relatively speaking. So therefore, it's going to be linear. So binary trees, there actually is a whole idea about how to make them more efficient by structuring them in a way to actually gain an advantage from the whole way in which it's structured, like ignoring left or ignoring right. And that's a completely different topic we will not be going into today because it's very complicated and this is still an introductory video. But I did want to kind of point out that just because it's a binary search tree does not always mean that big O is log of n. I did want to show you a counterexample to that. All right, let's code up this search function so that we can see it work in Python. All right, let's use Python and actually implement the find method for a binary search tree. So at the top, you'll see I have a class called tree node. I need a class to essentially say, okay, each node has a value, has a left child and a right child, and I'll set those to none initially. So basically, if we reach the leaf, then both of the left and right will be none. And then I also have a test tree that we're going to be using later, which starts off with a root, and then it will have just left and right nodes all the way down, so that way we can use it for testing. And what we're going to do is we're actually going to implement the find method. So what we're going to do is we're going to say current is equal to root. Okay, so essentially this BST find method will be given the root node of the binary search tree, and then what number do we want to actually search for. We're going to start off at the root. We're going to start off at the very top, and I think a while loop makes sense here, mainly because we just have the root node. We actually don't know how large the tree is. It could be like a bajillion nodes for all we know. And so I just kind of want to continue down until I either find the target I'm looking for or I reach the end. Okay, so we're going to just iterate till we hit a brick wall. And so since we don't know how many times we're iterating, while loop makes the most sense. All right, so honestly, this is very straightforward. If the node we're on, its value is equal to target. So basically we found it, okay? So like the current node we're on, we basically found it and we're like, hey, I found it, awesome. And we'll just, okay, return true, okay? So we found what we were looking for. Else if the target is less than the current dot value. So remember the problem is that if on the left child will represent a lesser value, so current is equal to current dot left. So what we're going to do is we're basically going to go to the left node. Otherwise, that means that the target is greater than the current value, and so we'll go on the right hand side, current dot right. And this while loop will continue. All right, we'll go down the left hand side if it's less than, we'll go down the right hand side if it's greater than, and if we find it, we'll return true. If we reach the end of the while loop without having found anything, we're just going to go ahead and return false, because that basically means that we got through the entire tree, we got to the leaf node, and we didn't find what we were looking for. So yeah, as you can see, this is not that bad, right? This is just basically a while loop with like if else, and it's really not that bad. All right, the main thing is, again, hopefully throughout the video you're understanding the basic logic. So these three statements are the three different conditions. Either we hit the target, it's less than the target, then we go left. If it's greater than the target, we go right. And so if we get to the end of the while loop and have not found our quarry, then we basically return false. So let's give this a try. And what we'll do is I will print BST find, and then we'll pass in the root node. And let's say I'm looking for 15. All right, so hopefully it finds it. So we'll do Python bst.py
true. All right, because I do have a node that's 15. And now let's do another test. Let's do 150. Okay, this should not, there is no 150, in which case I get false. All right, and so you'll notice that actually that's really blazingly fast. Okay, so again, this is logarithmic time. All right. Again, remember that to get the big O of log of n, then the tree needs to kind of be in the correct shape. So if it's all like one line, you're not getting any benefit from using a binary search tree. And you have to do things like what's called rebalancing a tree, which is out of the scope of this video. Maybe later on I'll talk about it. All right. But as you can see, the iterative way of doing this is actually pretty easy. Just a while loop with some if statements and then a return statement. Then you can use all the power of binary search trees to make your searches faster. All right, I hope you enjoyed the video, and I hope I have other videos on data structures and algorithms. If you enjoyed those, please take a look at the playlist, and I will catch you next time.